stability. And we're going to look at two types of colloids, hydrophobic and hydrophilic colloids. But it's important for us to have stability in our colloidal dispersions. Maybe somebody can start us off. Do you think stability is important? Remember, some of these colloidal dispersions are also pharmaceutical products. Pharmaceutical that colloidal dispersions. Is my voice clear? Hello? My voice is clear. Excuse me for that. Let me try to. Once again, am I clear? Is my voice back?
It's better now.
Better. You can hear me. Daniel Wambua?
Yes, I can hear you.
Okay. So Daniel, maybe you can start us off. Why do you think stability in our colloidal dispersion is of importance, especially when we are looking at it from a pharmaceutical view?
Okay. Well, let's take, for example, our colloidal system is a drug. So for the drug to be active for a long period of time, we need the stability, because, well, if it's not stable, well, to maintain the do you call it, the effectiveness of the drug, like the stability is needed. Yeah.
Okay, and what will cause instability in our colloidal dispersions? My voice is breaking, huh?
Yeah. Okay. Well, even from your end, Dr. I think still the voice is not that clear. I think there is an
Even
issue.
now?
Yeah.
There is an issue with internet, eh?
Yeah.
Clear
I
now?
guess. Okay. Sometimes you are clear, and then after some time, it's shaky.
Okay. Just let me know. But I can see now you're back.
Okay.
Yeah,
So the instability can be attributed to one, environmental factors, like, yeah, if you expose the system to too much heat, light, yeah, it can cause the instability due to breakdown of chemical bonds. Yes.
Today we have a challenge. Okay, it's time to though, as we go through the lecture, we'll see how instability may arise in colloidal systems. Is my voice back? Today network seems to be a challenge, eh? Are you to me?
Well, I think, Dr. there is still an issue from your end, if not my end.
Okay, maybe I can try logging in again. Can just give me some time. But now it's back.
Yes.
Now it's back. Okay, let me
Yeah.
just know when okay? Let me just know. You can alert me by texting so that I don't end up speaking to myself. I can see one of you has disappeared. You are 30 now, you are back to 20. This is a challenge with online classes. People feel like they can just miss, can just miss out and get the notes later. Anyway, you should be aware that we also take attendance. The attendance is taken online, so we know those people who attend class and those who miss. And there are consequences for failing to meet the minimum threshold of class attendance. Okay, so just as a basic introduction, we know that some of our pharmaceutical formulations will fall in the colloidal range. And because colloids are a dispersion of the dispersed phase particles dispersed in a continuous medium, we desire to prevent these particles from coming together. That is aggregating, or rather coagulating. Coagulating now is a form of colloidal particles aggregating together. This is because when colloidal particles come together and aggregate, this may result in what we call caking in suspensions. You know, caking is not a desirable phenomena for a suspension. When a suspension forms a cake, it will be very difficult to redisperse and dispense to the patients. Now, for emissions, this aggregation may lead to what we call whereby that your dispersed phase particles separate out from the continuous phase and form a layer on top of your emulsion. And this will be dependent on the density of the dispersed phase relative to the dispersion medium. We always desire a situation whereby we form loose aggregates, which we call flocks, that can easily be redispersed and be easily redispersed upon king, so that you can dispense your drug to the patient. This you'll cover more when you'll be looking at the formulation of suspensions and emulsions, I think in year 5. So this issue of aggregating is what we do not desire to occur in our colloidal system. Remember, the particle size range in our colloidal system is between 1 and to 0.5 microns. So these particles tend to undergo what we call Brownian motion, and they tend to stay far apart from one another. However, when aggregation occurs, it may result in what we call colloidal instability. So this is what I've been talking about. So in your initial state, move to slide 4. Something happening here. Anyway, it's okay. Can you look at it? So when you have your colloidal system in the initial state, this is what happens, whereby you find that your particles will be undergoing what we call random Brownian motions. So they tend to be far apart from each other. But now when they aggregate together and sediment to the bottom of the vessel, they form what we call a cake. So this is what this sedimentation will appear when your colloid system aggregates to form a sediment. And now creaming is where now the dispersed phase particles separate out and settle at the top of the dispersion medium of your colloidal particles. However, the desired state that we desire for colloidal systems is to form aggregates, which we call floc, through a process called flocculations. These loose aggregates on redispersion, they easily separate out instead of forming a dense cake or a compact cake. So we look at some of the definitions that are associated with colloidal instability or colloidal stability rather. So coagulation, whereby your colloidal particles will permanently aggregate to form a coagulum that is densely packed. And in this case, redispersion is not possible. Dispersion is not possible. So if you have a pharmaceutical suspension that undergoes what we call coagulation, this suspension will not be suitable to dispense to a patient. We also have creaming, but in this case now your dispersed phase particles separate out to form a layer on top of continuous phase or the dispersion medium. So in this case also, the dispersion is not possible, or rather is very difficult. So creaming and coagulation is a form of actually caking, will result in colloidal instability. I can see people are disappearing on, I don't know what is happening. You're also experiencing network challenges. These people who are disappearing, there are people who are disappearing and appearing, You're also experiencing network challenges. Okay, so our system, what we decide is to form what we call flocks through flation, so whereby you have loosely colloidal materials that can be easily reduced. And this can be done even by the patient upon shaking the bottle of the suspension. So upon shaking, this will disperse. The formulation can be dispensed to the patient. So of what relevance is colloidal stability to the patient? So you've seen two aspects of instability where you have coagulation and creaming. So remember, whenever a coagulum is formed or a cake, a dense compact cake is formed, the visual appearance of the product or the formulation to the patient may indicate quality or stability issues with the patient. So look at a suspension that has undergone caking. Just by looking at it, patient may be able to suspect that either of poor quality, the product has stability issues, and these may affect the compliance of the patient. The patient may not desire to take the medication. And in terms of seeing, when you form a compact cake or a coagulum that cannot be redispersed upon shaking, remember, your dispersed phase particles are the ones that will be containing the drug. So when the drug particles can be redispersed, find that the dosing will not be uniform. You'll have lesser of the drug in your continuous phase, the dispersion medium, and therefore dosing will not be uniform. So whenever you are dispensing product that has undergone creaming or caking, you'll have what we call an uniform dosing from the first dose to the last dose. And this uniform dosing may result in treatment failure. So that is how important colloidal stability is as far as pharmaceutical formulations are concerned. So let us now look at the relevance of the submicron particle size as far as colloidal stability is concerned. So you'll find that colloidal particles will be in the range of 1 nanometer to 0.5 nanometers. And these particles, as we've seen from our previous lectures, tend to undergo rapid Brownian motion, which prevent them from settling. So the particles will be in a continuous state of random motion and therefore do not settle easily. So therefore, this is very desirable. Yeah? Random movement due to the collision will be desired to prevent what we call colloidal instability or aggregation, especially where the Brownian motion offsets the force of gravity. So your particles will not settle easily. But there is a small challenge also as a result of the small size of the particles. Results, a very surface. Frequently also results in high free energy. So the particles will tend to have high free energy, and therefore the system will be in a state of what we call entropy disorderness. Therefore, the system itself will tend to lower the free energy to have some orderliness, so that the system becomes in an orderly state. And this is done by the tendency now to bring the particles close together to reduce the very large surface area. When the particles are on their own, they tend to have a very large surface area. And therefore, these particles will tend to aggregate so that they can reduce the large surface area and the high free energy to achieve some form of orderliness. So the system will tend to lower its free energy by aggregating, by trying to aggregate. And therefore, you must introduce stabilization mechanism in a colloidal suspension to prevent the aggregation and hence maintain your particles apart to ensure stability in a colloidal system. So we need stabilization mechanisms whenever we are preparing colloidal dispersions so that we prevent the aggregations of these particles and keep them apart. So the system itself also tends to the surface area by aggregating so that it can achieve some form of orderliness. Now we have a theory called the DLVO theory that talks about the mechanism behind the creation of colloidal particles. So this theory was proposed by 4 scientists, 2 who happens to be Russian physicists, and the other 2 who are Dutch chemists. So according to the DLVO theory, the forces on colloidal particles in a dispersions are as a result of electrostatic pulsions. So we have electrostatic forces, and also we have London type van der Waals attraction forces. So colloidal particles will be subjected to two of these forces, repulsive and active forces. And these forces will result in potential energy of repulsions and attraction between the particles. So colloidal particles will have these two forces. When they try to come together, there will be attractive forces and repulsive forces. So the net total potential energy interaction will be given by the summation of the van der Waals attractive forces and the electrostatic repulsive forces. So this diagram just illustrates, or this is a graphical illustration of two colloidal particles that are to come together. So on the y-axis, you have the interparticle distance, the distance between the two particles. And on the x-axis, you have now the energy of attraction and repulsion between the two particles. So remember, we said the two particles will be subjected to attractive forces. So this graph, the lower graph, forms the van der Waals attractive forces. And we have the upper graph, the one that is black in color, which forms the electrostatic repulsive forces. So it is the interaction of these two forces, the repulsive and attractive forces, that will form this composite curve, the one that is a bit pinkish in color. When these two forces interact, they form composite curve. This is now the VT, the total force of interaction of the repulsive forces and the reactive forces. So at the primary minimum, at this point, we have the attractive forces being greater than the repulsive forces. So at this point, you'll find that the particles do not aggregate. The particles will oh no, when the particle will aggregate actually when the forces of attraction are greater than the repulsive forces. So at the primary minimum, you tend to form aggregates, or actually what we call coagulation or sedimentation of your particles. The particles will closely aggregate to form a coagulum or a dense compact sediment. So at this particular point, this point where the repulsive forces are greater than the attractive forces, your particles will tend to stay apart. So you'll have what we call a deflocculated state, a deflocculated state of your dispersion. So your particles will tend to stay apart from one another. But now, as a result of the interaction of the attractive forces and the repulsive forces, we have what we call the secondary minimum. Secondary minimum, which is the point at which the active forces closely offset the repulsive forces. So at this point, you find that your particles tend to loosely aggregate. So at this point is where we form what we call the floccules, the loose aggregates, which upon shaking, they can be redispersed. So we also have a potential barrier upon which must be exceeded particles to interact. So this is the energy barrier that must be exceeded by the two interacting particles so that they can aggregate together. So this is what I was just trying to explain now. This is the composite curve as a result of the two forces of attraction, repulsive and van der Waals attractive forces. So at the secondary minimum, this is the point at which you form loose floccules, whereby your attractive forces interact the repulsive forces. So you're able to form loose floccules, which upon dispersion, redispersion, you can easily redisperse upon shaking. Now at the primary minimum is where now you form your dense compact coagulum or dense compact coagulation, whereby the attractive forces are much, much greater and outweigh the repulsive force. And at this point is where now you have a deflocculated state, whereby the repulsive forces are much greater than the active forces, and therefore your particles will tend to stay apart, far apart from another. They do not interact. 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 So how do attractive forces arise? So the van der Waals forces of attraction may be due to dipole-dipole interactions between the particles, also dipole-induced dipole interactions, and also due to induced dipole-induced dipole interactions. I hope my voice is clear. I'm not breaking, so we are moving together. Now, repulsive forces will arise from like charges. So whenever you have charge on the particles, they'll generate electrostatic repulsive forces. So whenever you have your charge, negative charge on your particles, because of the light, they'll tend to repel one another. So due to mutually repulsion of these particles, that these will prevent particles from approaching closely enough to aggregate. So if you are able to reduce the charge on the particles, you will tend to increase the likelihood of aggregation. So you can be able to modify it or reduce the charge on the particle by the pH of your dispersion and the ionic composition, or by introducing surfactants. So by reducing the charge on the particles, you tend to increase the likelihood of aggregation due to reduction in repulsive forces. Now this brings us back to the zeta potential. Remember we talked about the potential at the shear plane, the slipping plane. So it has been found that by increasing the potential, increase also the electrostatic repulsion between particles. By increasing the charge, and therefore the zeta potential, you tend to increase the electrostatic repulsion between the colloidal particles, and this helps to improve stability. So the converse is true also. By reducing the zeta potential, you tend now to increase the tendency for colloidal particles to aggregate. So for most stable colloidal dispersion, you find that they tend to have a zeta potential of plus or minus 30 to 50 millivolts to form for your stable colloidal dispersion. So what is the effect of ions on the zeta potential? What is the effect of ions on the zeta potentials? So when you add ions or electrolytes, you're able to change the zeta potential of colloidal particles. And it has been shown that ions of opposite charge will tend to reduce the zeta potential. When you add ions of zeta opposite charge, you'll tend now to the electrostatic repulsion, and therefore by that affect the zeta potential to the point whereby aggregations of your colloidal particles will occur. So when you introduce ions of opposite charge, you reduce electrostatic repulsive forces. Therefore, your ions now tend to, your colloidal particles to come closely together. Now, the valence of ions of opposite charge is the effectiveness of the ions in causing the aggregation. So, depending on the valence of the ion of opposite charge that is being introduced, will tend to affect how effective the ion will cause aggregation. So, by increasing the ion valence, and remember this is the ion valence of opposite charge, you will also tend to increase aggregation power, or rather the coagulation power. And this is what is referred to the Schulz-Hardy rule. So when you increase the ion valence of opposite charge, you also tend to increase the tendency to aggregate, or rather the coagulation power, according to the Schulz-Hardy rule. According to the Schulz-Hardy rule. So now that was a brief overview on stability of colloidal dispersions. So we can look at hydrophobic colloids. Remember, hydrophobic colloids tend to be thermodynamically unstable. They will tend to aggregate, and therefore require stabilizing mechanisms. So whenever you are formulating a product that is a hydrophobic, you will tend to stabilizing mechanisms to get the stability of dispersion. Stability of your dispersion. How do we stabilize hydrophobic colloids? We have two approaches. One of them is what we call steric stabilization. And this you simply do by adsorbing molecules on the surface of the colloid so that you are able to barrier that prevents the particle from approaching closely enough to aggregate. So you adsorb the particle on the surface of the particle to form a barrier. Adsorbed molecules will prevent the particles forming closely together. Prevent the particles from coming closely together so that they are to aggregate. So steric stabilization results from adsorbed molecules that form a barrier, prevent particles approaching closely enough to aggregate. It may also be as a result of repulsion due to the reduction of entropy when adsorbed molecules overlap. Remember, the system will tend to lower the Gibbs free energy by forming aggregates. So whenever you have adsorbed molecules on the surface of the cores, these particles will not aggregate. As they to come close together, they'll tend to overlap, and as a result, there'll be reduction of entropy. There will also be repulsion due to an osmotic pressure when these adsorbed molecules overlap. Adsorbed molecules must also be soluble in the dispersion medium. And a good example is we use polymers or surfactants. We adsorb polymers or surfactants onto the surface of the particle. So this is just a simple illustration of the steric stabilization. So when you adsorb your polymers or your surfactants onto the surface of colloidal particles, so they'll prevent these coming closely together. So these particles will tend to overlap whenever they try to come together instead of aggregating. That's simply what steric stabilization looks like. The other approach is called electrosteric stabilization. And this involves the introduction of ionic groups on the surface of colloidal cores. So you still have your adsorbed polymer groups, but you further introduce ionic on the surface of colloidal particles to counterbalance the van der Waals forces of attraction in the colloidal particles. So for your system to maintain electroneutrality, remember when you introduce ionic groups, an equal number of counter ions with opposite charge will tend to surround your colloidal particle and give rise to an overall neutral charge of the double layers. And therefore, this mutual repulsion of these double layers surrounding the particles is what will result in colloidal stability. So your colloidal double layers will tend to repel one another. So this is how it looks like. Now this diagram has a mistake. Now it will be the counter ion. So the particle is supposed to now to be surrounded by positive charge. And now this positive charge that will tend to repel one another. So electrosteric stabilization combines both steric stabilization and the introduction of ionic groups on the particles that will attract counter ions that will tend to repel one another for the system to achieve stability. For your system to achieve stability. So this should be a positively, the counter ions will be positive in nature. So how does steric compare to electrosteric stabilization? Steric stabilization, you'll find that they tend to be insensitive to the reaction of electrolytes. Electrosteric stabilization, because they involve the introduction of ionic groups onto the particle surface. So with this mechanism, it is very sensitive to electrolytes. Steric stabilization is equally effective in both aqueous and non-aqueous division. In this case, you're only adsorbing polymers onto the particle surface. However, for electrosteric stabilization, it's mainly active in aqueous dispersion. In aqueous dispersion where action can occur. For steric stabilization, it's equally effective at both high and low solid contents. But for electrosteric stabilization, it's only effective at low solid content. So we normally apply steric stabilization when we have reversible flocculation or dispersion. But for electrosteric stabilization, we prefer it to have irreversible coagulation. Form dense coagulums, dense compact columns. Now, would freeze thaw stability. I believe you all know what thawing means. But for electrosteric stabilization, it has poor freeze thaw stability. So we also have two phenomena that affect hydrophobic colloids or are associated with the stability of hydrophobic colloids. We have what we call sensitization and protection. So sensitization involves the introduction of, or rather the addition of, a small amount of hydrophobic or hydrophobic colloid of opposite charge to your dispersion, and this tend to increase the tendency for coagulation, and this because it reduces the zeta potential. Remember, when you introduce ions of charge, reduce the repulsive forces between the particles of the zeta potential. So sensitization to promote colloidal instability, or rather what we call coagulation of your hydrophobic colloids. On the other hand, we have what we call protection, and this is in addition a large amount of hydrophilic colloid that gets adsorbed the surface of the colloidal particle, and these result what we call steric stabilization. So when you introduce a hydrophobic colloids onto the surface of hydrophobic particles, you achieve what we call steric stabilization. The colloidal particle adsorbs onto the surface of the hydrophobic colloids, and this prevents the particles from being closely together from aggregating. So this is just a grammatic illustration of the two phenomena of sensitization and protection. So in A is you have protection, so you have your colloidal particle that had adsorbed hydrophilic colloid onto the surface. This prevents particles from coming closely together, but rather from meeting. On the other hand, we have what we call now sensitization, by introduce a hydrophobic colloid with charge, and therefore particles tend to aggregate. Your particle tends to come together because of the reduction of the zeta portion. So let's look at some of the factors that may result in stabilizing of hydrophobic colloid. So we have the particle size. So remember, most colloidal dispersions will have the submicron size that is responsible for prevention of settling. Particles are always in continuous motion. However, remember what you said, the large specific surface area of the small particles always facilitate interparticle interactions, and this is because in a bit to reduce the entropy due to the high Gibbs free energy. The particles, by increasing the charge on the particles, you tend to reduce aggregation. However, when you decrease the charge on the particle, you tend to promote aggregation. Surfactants, the introduction of surfactants may result into both steric and electrosteric stabilization, as they adsorb onto the particle surface and prevent the particles from coming close together. Instead, they tend to overlap. pH for dispersion. The pH can be responsible altering the surface property by changing the ionization of functional groups, or even by binding onto surfactants, the binding of surfactants. So when you increase the pH of your colloidal dispersion, you tend to lead to an increased surface charge due to ionization. Remember, when you increase the surface charge, you tend to increase the zeta potential, and therefore you tend to promote colloidal stability. Viscosity of your dispersion will affect the amount of dispersed particles, and as a result, when you increase the viscosity, you tend to slow down the Brownian motion of your particles, and this will promote your particles coming together. When you use Brownian motion, your particles will to aggregate. Now, electrolytes can also destabilize hydrophobic colloidal charge. Colloids by charge neutralization, when you introduce electrolytes of charge, or what we call double layer compression. Remember, your colloidal dispersion will be composed of a double layer. Each colloidal will be composed of a double layer. So when you tend to neutralize the charge, these double layers tend to come closely together, so they tend to compress the double layers. The particles tend to aggregate, And as they come closely together, their double layers are compressed. So this will be the effect of reduction of opposite charge. The effect of water-soluble polymers can stabilize or coagulate hydrophobic colloids depending on the nature of interaction and concentration. So in case of coagulation, this will occur when there is what we call charge neutralization. Charge neutralization occurs as a result of the introduction of water-soluble polymer. The dispersion will tend to undergo coagulation. We also have the effect of insoluble additives. So the end of insoluble additives may also lead to interactions with hydrophobic. If it is result in coagulation. So when you introduce insoluble additives of opposite charge into hydrophobic, will also tend to reduce the zeta potential and promote aggregation of the colloidal dispersion. So how about hydrophilic colloids? Hydrophilic colloids tend to be thermodynamically stable. What we call solvation, whereby there is interaction between the solvent and dispersed phase particle, the solute. And this solvation normally is what we call a solvent sheath. There's a layer that forms onto the particle surface as a physical barrier between hydrophilic colloids. So this layer promotes stability because it prevents the interaction of the hydrophilic colloidal particles. It also reduces interfacial tone, and as a result, it also reduces the driving force for aggregation. So solvation is the property of hydrophilic colloids because it's a protective mechanism that prevents the aggregation of colloidal particles. Now, what will be the effects of ions on colloids? Now, when you add ions in high concentrations to a hydrophilic colloids, it will tend to result in what we call precipitation or gelling out of the hydrophilic colloid. And this is what we call salting out. Now, when you introduce ions, they will tend to the solubility of the dissolved colloids, the competition of the ion, the amount of water available for dissolution. So the ions or the electrolytes will compete for the water of hydration, and as a result lead to precipitation or gelling out of the hydrophilic colloid through the mechanism called salting out. So the ions compete for the water of hydration that is present, colloidal dispersion, and as a result, they tend to precipitate out the hydrophilic colloid. So still on the effect of ions, we have what we call Hofmeister or the iotropic series that arranges these ions in their order of effectiveness in causing precipitation of hydrophilic colloids. And this is normally related to the hydration of the ion. So for anions, we have citrate, this order greater than tartrate, greater than sulfate, greater than acetate, greater than chloride, greater than nitrate, greater than bromide, greater than iodide ions. So this is the series for anions, whereas for cations we have magnesium greater than calcium, greater than, I don't know which symbol is this, strontium, I think it's sodium, which is greater than barium, lithium, sodium, potassium, rubidium, and caesium. So it's a series that arranges the ions in their order of effectiveness in causing precipitation of hydrophilic colloids. So how does the effect of ions compare to hydrophobic colloids versus hydrophilic colloids? So you'll find that for hydrophilic colloids, you require a level of ions to cause precipitation as compared to hydrophobic colloids. Hydrophobic colloids you require lower levels when you want to cause gelling out or precipitation. Now for hydrophilic colloids, the gelling out or the precipitation gelation is often reversible. So, and this is reversible by the removal of the salt or the ion. Remember in our last lecture, we talked about dialysis. So you can dialyze your dispersion to remove the ions and therefore reverse the precipitation of hydrophilics. Also by addition of water. Remember, these ions compete for the water of hydration. So when you add more water to your dispersion, you may be able to pass the precipitation or the gelation of your hydrophilic colloid. However, for hydrophobic colloids, this gelation or precipitation is very difficult or even irreversible in most cases. So what happens when you mix two hydrophilic colloids? So when you mix two hydrophilic colloids of opposite charge, this may lead to aggregation. Remember, that you attract aggregation and eventually the separation of your colloidal dispersion into a layer rich in colloidal material. A layer rich in colloidal material. This phenomenon, we call it coacervation. So coacervation occurs when you mix two hydrophilic colloids of charge. And this colloidal rich layer is what we call the coacervate. It's what we call the coacervate. So an example is gelatin and acacia. So gelatin is positively charged and acacia is negatively charged. So when you mix them, find that there will be separation of a colloidal rich layer as a result of aggregation of the two colloidal dispersants. So as we come to the end of our lecture for today, there's a small assignment for you people on some of the methods that we can use to assess colloidal stability. So I've just outlined them here for you. So you're supposed to do a small write-up on how you can carry out colloidal stability using visual observation. Visual observation, an attempt from the class before you do the assignment. How can you carry out colloidal stability using visual observation? I have not lost you along the way due to my voice breaking. Can we brainstorm together? Somebody is talking about observation for caking. That is true. You people don't want to speak. You are typing. Caking or creaming. That is true. Yeah, you can observe for collation, caking, creaming. What about microscopy? How can you assess colloidal stability through microscopy? Microscopy? Okay, you'll do this assignment. So quantitative methods, we have particle size. You use these methods to determine the particle size, diffraction, autocorrelation, spectroscopy. You also have spectroscopic methods, electrochemical methods that involve zeta potential measurements. We have sedimentation, filtration, and rheology. How can you use rheology to determine colloidability? You are typing. Why can't you speak up? Amina Bashir. Saying velocity, that is true. So you know the answers. It's only that to. What about filtration? Filtration, an attempt for class.
Hello,
Yes.
can you check for residues?
So which is, and you will do assignment. So you try and find out. And please, this assignment I'll mark it as part of your assessment. So this assignment is due on Wednesday next week. I'll organize with the class rep on how to collect it. These are very short, also use the assignment as part of continuous assessment. So the assignment is important. And also I want to remind you that you'll also find a question in the CAT or even in the exam on boards for assessing colloidal stability. So take this assignment seriously. Take this assignment seriously. I've already given you a roadmap. So it's just you to go and fill in the rest of the details. So unless there is a question or a concern, I'd like us to stop there for today. These people are not attending online. Just note that we have the attendance list. And actually, it's permanent. Computer. This is an attendance list that can even assess 10 years. So I can easily note some people that are not there today. Easily know some people are not there today. So we stop there for today. Do this assignment and make sure when you're handing to the class rep, you sign. There has to be somewhere that you sign against your name that you handed in the assignment. So I'll be collecting it on Wednesday next week. Okay, we can there for today.